So in the last class, we discussed about the concept of MIMO. So what is MIMO? So in the last class, we discussed the concept of MIMO. What is MIMO? What is the full form for MIMO?
Multiple input, multiple input, multiple output.
Yes, it is multiple input, multiple output system. So it means that there will be n number of transmitter and n number of receiver. Okay. And we also saw the block diagram of a MIMO system. So if you see in the MIMO system, so you will be having the transmitter and the receiver. So there will be some n number of transmitters, that is transmitting antenna, and there will be some n number of receiving antenna. Okay, so for example, let us assume it is having a T transmit antenna, T transmitter, and R receiver antennas. So the signal will be acquired by all the antennas. Okay, from the transmitter, whatever the signal is transmitted, it will be acquired by all the antennas. Similarly, like this. So this is a MIMO system. So what is the advantage of this MIMO system? So the advantage is so it increases what? The reliability of the signal through diversity. It increases the reliability of the
Speed
signal.
also increases,
Yes,
no ma'am?
exactly. The second point is that. Okay. So the data rate, second point is that the data rate of the wireless communication system will also be increased. Okay. So we also saw what is called as a spatial multiplexing. What is spatial multiplexing? What is spatial multiplexing? See, here we are transmitting the data in parallel, several data in parallel. That is a stream of information is transmitted in parallel. Okay. So this is called as spatial multiplexing. All right. So here what we are doing, we are transmitting several information stream in parallel. So this is also called as, this is termed as spatial multiplexing. And we also saw the system model of MIMO channel in the last class, right? So now we will see about OFDM, that is MIMO and OFDM combination. MIMO and OFDM. It is nothing but it is combining these two technologies. We are going to combine MIMO and OFDM. So why we wanted to combine this MIMO and OFDM is that to achieve higher throughput. So we are going to now see how to combine this MIMO technology and OFDM technology to achieve much higher throughput. So the motivation behind this MIMO, if you take this MIMO, so it is to achieve higher throughput, and this is to achieve higher throughput. And if you take this OFDM, okay, so this OFDM, what it does is that it converts a frequency selective into a flat fading, okay, parallel flat fading set of channels. It converts frequency selective to flat fading set of channels. All right. So when we couple this MIMO and OFDM, okay, when we combine MIMO and OFDM, what we can achieve is that we can achieve the throughput, higher throughput, as well as we can achieve this flat fading set of channels. So we can achieve both higher throughput and flat fading by coupling this MIMO and OFDM. Okay. So MIMO OFDM is just a combination of MIMO technology with the OFDM technology. Okay. So MIMO OFDM, it will convert a frequency selective, okay, frequency selective MIMO channel into multiple parallel flat fading MIMO channels. So when we are going to combine this MIMO and OFDM, it will convert what? It will convert the frequency selective MIMO channels. If you take this MIMO channels, they are frequency selective in nature. So it will convert with, along with OFDM, what it does is that the MIMO frequency selective channel gets converted into a parallel flat fading MIMO channels. Okay. So hence this MIMO OFDM, it significantly simplifies the baseband receiver processing by eliminating the need of a complex MIMO equalizer. So basically, if you want to convert this MIMO channel into flat fading, we may require a MIMO equalizer. So instead, by using this combination of OFDM, it will eliminate the need for a complex MIMO equalizer. Okay, so if you take this MIMO frequency selective fading channel, it will causes the MIMO intersymbol interference. So if you take the normal MIMO channels, it will causes the ISI, that is intersymbol interference. So it will causes the intersymbol interference. So hence, in the presence of MIMO intersymbol interference, okay, so we need to go for a MIMO equalizer. We need to go for a MIMO equalizer. So if you normally take this MIMO channel, it will produce this intersymbol interferences. So in order to avoid this, we need to go for this MIMO equalizer. Okay. So by using this combination of MIMO with OFDM, it will remove the need for the MIMO equalizer. Okay, so this will significantly simplify the baseband receive processing. That is, it will eliminate the MIMO ISI. So by using this combination MIMO OFDM, it is going to eliminate the intersymbol interference. Okay, so first for this, to understand this, let us take the frequency selective. Let us take the frequency selective MIMO channel. So let us take the equation of MIMO frequency selective channel. So first we will consider the frequency selective SISO channel first. We will first take the frequency selective single input, single output channel, which is modeled as, it is actually modeled as an FIR channel filter. So the system model for the single input, single output channel is system model. It is given as Y of K equal to L is equal to 0 to L minus 1, H of L, X of K minus L plus N of K. Okay. So if we are going to expand this, so when I substitute L equal to 0, we get it as Y of K equal to h of 0 into x of k plus h of 1 into x of k minus 1. So like that till n of k. So here if you see what is this? This is actually the channel coefficient h of L. This is the transmitted signal and this n of k is the noise. So this is what is received. Y of k is nothing but the received signal. So y of k is the received signal. Okay, so when we expand this, this first term represents, that is h of 0 into x of k, it represents the current symbol which is getting transmitted. Along with that, we are going to get the past symbols as well. H of 1, x of k minus 1 is nothing but the past symbol. Okay. So at the receiver end, we are going to get the current symbol with the past symbol. Okay, this is actually called as inter-symbol interference, which we have already discussed in OFDM. Okay, so this is called as the inter-symbol interference. So when we at the receiver end, we get the current symbol along with the past symbol, then it is the inter-symbol interference. So hence, if you take a MIMO frequency selective channel, okay, this is for SISO channel. This is SISO channel equation, and we are seeing what is this inter-symbol interference. Instead, similarly, if you take the MIMO frequency selective channel, MIMO frequency selective channel. Again, it can also be modeled in the form of FIR filter. So here it will be like y of k bar. That is, it will be a vector. Y of k bar equal to summation L equal to 0 to L minus 1. H of L x bar of k minus L plus n bar of k. So this is nothing but the received R by 1 symbol vector. Okay, this H of L is nothing but the channel matrix, MIMO channel matrix. Okay, which is corresponding to Lth tap. This is channel matrix corresponding to the Lth tap. And this one is the transmitted signal. Okay, transmitted k by 1 symbol vector. It is transmitted k by 1. Minute. It is transmitted k by 1 symbol vector, and this one is the receiver noise, that is R by 1 receiver noise vector. So this channel matrix, if you see H of L, it is nothing but it is R by T matrix. That is the channel MIMO channel matrix. So this MIMO frequency selective channel, so it is modeled in the form of MIMO FIR filter, which is y bar of k equal to L to 0 to L minus 1, H of L, x bar of H minus L plus n bar of k. So again, if we are going to expand this and write it, so if we expand this and write, what we will get, it will be y bar of k equal to H of 0 x bar of k plus h of 1 it will be h of 1 x bar of k minus 1 plus h of 2 x bar of k minus 2 like that till h of l minus 1 x bar of k minus l plus 1 plus n bar of k. So here also if you see this first term, that is h of 0 x of k, x bar of k, it is nothing but the transmit vector. It is a transmit vector at time t. It is a transmit vector at the time t. And similarly, if you take this h1 x bar of k minus 1 is nothing but the transmit vector at time t minus 1, that is a previous symbol. Okay, so like that. So if you take this MIMO frequency selective, the FIR filter model, even here if you see, this is actually the inter symbol vector interface. It show interference. So it shows the inter symbol vector interference. So if you take this y bar of k, it depends on the transmit vectors, that is x bar of k minus 1 till x bar of k minus l plus 1. Okay, so these are all nothing but what? Which are the previous transmit symbol vectors. Okay, so these are all the previous transmit symbol vectors. So hence, this is an L tap frequency L tap frequency selective MIMO channel. So it is an L tap frequency selective MIMO channel. So hence in MIMO frequency selective channel, so this ISI occurs between the current and previous transmitted symbol vectors. Okay, so this intersymbol interference occurs between the current and the previous transmitted symbol vectors. Okay, so if you take in a MIMO OFDM system, so if you take in an MIMO OFDM symbol, so one needs to perform this inverse discrete Fourier transform or inverse FFT fast Fourier transform operation at each transmitting antenna. So now we are going to combine this MIMO and OFDM. So we will see the transmitter schematic of this MIMO OFDM. We will see about the transmitter schematic of this MIMO OFDM. So what this OFDM does, it will convert the frequency selective into a flat fading channel, right? And also MIMO, it will increase the throughput. So now we are going to combine both this MIMO and OFDM. So if you remember the block diagram of OFDM, so let me just put down this block diagram of OFDM. So whatever the input symbol we are getting at, so it gets converted from serial to parallel. Then what we do, we give it to an inverse fast Fourier transform, that is endpoint inverse fast Fourier transform. Then these signals will further get converted from parallel to serial, and then we will be adding the cyclic prefix, and that would be transmitted. Okay, similarly at the receiver end, what will happen? The signal will get converted to parallel, serial to parallel. Then here what we will do at the receiver end, here if it is inverse Fourier transform, here it will be, we will be just taking the fast Fourier transform of it, and then this gets converted again from parallel to serial, and this goes to the receiver. Okay, so here we are adding the cyclic prefix. Similarly, at the receiver end also, we need to remove this cyclic prefix. So the cyclic prefix would be removed, and then the signal will get reconstructed at the receiver end. So now what we are going to do is that we are going to combine this MIMO and OFDM, and we are going to see the transmitter schematic. Okay, so let us assume these are the symbols that are arriving. So these symbols will go through the first step, that is serial to parallel. Serial to parallel demux for transmit antenna. We are just going to combine both the technologies, MIMO and OFDM. Okay, so these symbols first will go through the serial to parallel demux. Further, so if you're having some n number of antennas, then these symbols further they go through another serial to parallel demux. See, we are going to consider some T number of transmit antennas. So if there are T number of transmit antennas, T number of transmit antennas, then you will be having T number of serial to parallel demux. So it means that this output of this serial to parallel, it's further, it is passed on to another serial to parallel. Okay. So now if you see each path, so if it is going to be this path, it is going to have the OFDM technology over here. So the serial to parallel will, the output of this will go through an endpoint IFFT, that is inverse fast Fourier transform. Similarly here, there will be endpoint IFFT. Similarly here also. It will pass through this IFFT. Okay, so this converted signal, what will happen here? Output of this IFFT, now it is ready for transmission. So it will be converted from parallel to serial mux. This converted signal will go through parallel to serial mux. Similarly here. Right? So once it is converted, then what we will do, we will be adding the cyclic prefix. Cyclic prefix would be added to it. So now it gets transmitted by the T number of transmitting antennas. So this is going to be the transmit, that is multiple transmit antenna. So this will be antenna, transmit antenna 1. This is transmit antenna 2. Similarly, this will be the transmit antenna T. So this is the transmitter schematic for MIMO OFDM. So we are combining the MIMO technology with the OFDM technology. Okay, so here, say for an example, so with this block diagram, we will take an example. Say, suppose we have n equal to 256 subcarriers. Say, suppose we have n equal to 256 subcarriers. Okay, and there are t equal to 4 transmit antennas. So t equal to 4 transmit antennas. Okay, say suppose if we wanted to, the input symbols, say for example, it is going to be 1024. So how many input symbols we are getting? We are getting 1024. So this 1024 input symbols are needed to be distributed among these 4 transmit antennas. It means that, so each channel, so here each channel will go through 256 symbols, right? So 4 channels are there. So 1024 divided by 4 transmit. There are 4 transmit antennas are available. So therefore, each channel will go through 256. So if you take this, yes, this will be having 256 subcarriers. Here it will be having 256 subcarriers, and here it will be having 256 subcarriers. So we are, what we are doing, we are dividing the 256 symbols among each of the 4 transmit antennas. Okay, so here we are dividing the 256 symbols among each of the 4 transmit antennas. Is that clear with the block diagram? Any questions in this? So here, if you see, we are transmitting these data 1024 symbols parallelly through the 4 transmit antennas. So we are considering n equal to 256 subcarrier, transmit antenna equal to 4, and there are 1024 symbols. So how we are going to transmit this 1024 symbols at a time is that number of transmit antenna is 4. So there will be 4 channels available. I mean, 4 path would be available. So 1024 divided by 4, which is equal to 256, and each path is having 256 subcarriers. So this 1024 symbols are divided into 256, four 256 subcarriers, and that would get converted and modulated, and the data would be transmitted through the 4 transmit antennas. Okay, so this is an example of MIMO OFDM transmitter schematic. Is that clear for everyone?
Yes, ma'am.
Okay, so now this is going to be the transmit section. So similarly, we will understand what is our receiver section is. Okay, so now we will understand about the receiver. That is MIMO OFDM receiver schematic. If meeting ends, please join back again. Okay, I think it will stop in some time. What I will do, I will stop this meeting here. I'll start the meeting again. Okay, because there is another diagram which has to be drawn. All right, please join back again. I'll just stop this meeting here.